Okay, now we're going to do a perfectly inelastic collision. And the way we know it's a perfectly inelastic collision is just by reading the problem. You've got a 90 kilogram signal relay floating in space, and it's struck by a 1,000 gram meteoroid. If you don't know what a signal relay is, you can look it up. It's basically, a type of satellite that's rotating, that's, you know, orbiting the Earth in space. So it gets hit by this meteoroid, and the latter embeds itself. That means the meteoroid embeds itself in the craft, and the two sail away at 5.0 meters per second. So, what was the initial speed of the meteoroid? Uh, if this thing's floating in space, I guess I should back up and say this. Apparently, the signal relay is not uh, orbiting the Earth; it's just floating in space. So it's just sitting there uh, in space, and it's struck by a 1,000 gram meteoroid. They two sail away at 5 meters per second, so they're together. They're combined after the collision. That's what tells me that it's a perfectly inelastic collision. So the conservation of momentum applies in this scenario, where initial momentum has to equal final momentum. Initial momentum of both objects together. So you've got the initial momentum of the, let's call it the relay, plus the initial momentum of the meteoroid has to equal the final momentum of the relay and the final momentum of the meteoroid. And you don't have to write this out. You could, immediately expand into the mv plus mv equals mv plus mv equation, which I'll do right now. I just, threw this in there just for good measure. So let's expand these. This expands to mass of the relay times velocity of the relay initial. This expands to mass of the meteoroid times velocity of the meteoroid initial. Again, this one expands to mass of the relay times velocity of the relay final. And this momentum expands to mass of the meteoroid times velocity of the meteoroid final. Now, because it's embedded into the craft, the meteoroid, and the two sail away at this speed, they're together, so their velocities are equal. So these two final velocities are equal to each other. So a lot of times people will just call it a new term. Some people will call it velocity Rm because you have the relay and the meteoroid together. So let's call it that. We're just calling it a new term, and we can plug that in for both of them and rewrite our equation. If we rewrite this equation and plug this in for both our velocities, here's our new equation, and we can rearrange this side of the equation because we have two identical terms here. So we can even rewrite it one more time or simplify it one more time. And here's our simplified equation. Now you could use this. This is really what any inelastic collision, where two things are coming at each other and colliding, will expand to. Object one, object two, object one, object two, and they're going to have the same velocity. Object one, two, so to speak, velocity one, two. So all of them will end up looking like this. Now, this is a more simplified problem because uh, our initial velocity of the relay is 0, so this whole term is 0. We have 0 plus plug in the mass of the meteoroid. That's 1,000 grams, which is 1 kilogram. That's 1 kilogram. So think about the 1 kilogram masses that we use in class, and you'll get an idea of what the size of that meteoroid is. And we want to find out what the initial speed of that meteoroid is. So that initial is what we're solving for. And plug in the two masses. Now we've got a 90 kilogram relay plus 1 kilogram meteoroid. So this relay is 90 times more massive than the meteoroid. So we're going to figure out what the new velocity is because, or what the initial velocity was based on the fact that they're both sailing away at 5 meters per second together. So now we can solve for the initial velocity of the meteoroid, and solving the initial velocity of the meteoroid is 455 meters per second. So that's a pretty massive speed for the meteoroid. And it needs to have a massive speed if it's going to move, excuse me, let's use a different word than massive, a very high velocity if it's going to move that relay. One thing we need to note is when you're solving this, keep in mind that when you're solving these types of problems, if I had a velocity for the relay, if they were going towards each other, one would be going one direction, one would be going the other way. You got to keep in mind the direction of your velocity. Okay, momentum is direction aware. You got to keep in mind what the direction of the velocity is when you're solving these types of problems. So there's an example. Hopefully it'll help you with the other inelastic, perfectly inelastic collisions.